Hi everyone, Kevin here, back with Worksheet 12 video number 2. We're talking about testing phenolics by Spectrophotometer. Video 1 was mostly background. Let's get into the experiment. What is a spectrophotometer? It's a fairly expensive instrument that is actually very simple in overall operation. It's just a source of light. We shine that light through a sample. In this case, it will be a sample of wine. And there's a detector in the instrument that measures the amount of light that passes through the sample. So we know how much light was emitted by the bulb. Once we detect how much passed through the sample, we know how much was absorbed by the wine. And we usually give that an abbreviation, simply A. So we'll take some wine and we will put it in a cuvette that looks like this. That fits into the spectrophotometer. We simply shine some light on that wine in the cuvette, and the detector will tell us how much was absorbed by the wine. The detector does the math for us, knows how much again was emitted, knows how much passed through and reached the detector, and the difference is the amount absorbed. So we have to think about dilution factors in doing this experiment. Spectrophotometers have a range in which they work best. Many spectrophotometers work in the range of 0.1 to 1. This is a unitless measure of light absorbance. Some spectrophotometers work up to higher absorbances. The one we're using in class actually goes pretty effectively from 1 up to 3.0. But what if your wine absorbs at a rate of 20 and the absorbance of the spectrophotometer is in the range 0.1 to 3? Well, we have to dilute the wine. Say we were at 20, our absorbance of our wine was approximately 20. If we had to get down below 3, we need to dilute the wine significantly. In other words, if we put the wine undiluted into the instrument, the absorbance would be way off the scale. The absorbance would read 3, but we wouldn't know if that was 3 exactly, or some number way higher than 3 that the spectrophotometer simply couldn't read. So we might dilute this. In this case, if we estimated our absorbance was around 10, we could do a 10 times dilution. That would take our absorbance down to approximately 2. And then we're in range of the spectrophotometer. So what is a dilution factor? Well, a 4 times dilution factor is actually 1 part wine, 3 parts water. So it's total 4 points, or 4 parts, sorry. So think of it this way. You have a beaker full of wine, and it is 100% wine. Now you take a little bit of that wine, 1 part wine, and put it in another beaker. So let's divide this beaker, the liquid, into 4 parts. So 1 of those parts is wine, and 3 parts are water. So 1 part wine, and the other 3 parts are water. So if this is 100% wine, what is our beaker on the right? Well, it is 25% wine. So the concentration is 1/4 of the pure wine. So, or 25%. So this is a 4x dilution. 4x gets us down to 1/4 of the original concentration. So a 4x is 1 part wine, 3 parts water, like we showed here. Okay, so just remember, it's not 1 part wine, 4 parts water. It's 1 part wine, 3 parts water. So what's a 10x dilution? That would be 1 part wine and how many? 9 parts water. So it's 10 parts total. And that gets the wine down to the concentration of wine is 10% of pure wine, of the wine by itself. So in our example above, if we were doing a 10x dilution to get in range of the spectrophotometer, we would do 1 part wine, 9 parts water. Okay. We are going to be pipetting small amounts of liquids. And so we use these micro pipetters. And there are 3 of them shown here. This is a typical set you'd find in a wine lab. The P1000, you'll see the designation on the handle there. That has a range usually from 100 microliters up to 1,000 microliters. So 1,000 microliters would equal 1 milliliter. So a microliter is 1/1,000,000th of a liter. So 1,000 microliters is 1 milliliter. Microliters. Okay, and it gives some of that information here. The P200 shown here, that has a range from 20 to 200 microliters. And the P20 has a range usually from 2 to 20 microliters. So we can be very exact about small amounts of wine or water or whatever other solution we're pipetting. So we're going to use these micropipetters in this experiment. Wine absorbs light at different wavelengths. And that's because there are different molecules in wine. And each molecule, each type of molecule will absorb light, or rather electromagnetic radiation, at a different wavelength. So some of the molecules will absorb way up in the microwave range, some in the infrared range, some up in the ultraviolet range, and some in the visible light range. And that's, of course, what gives wine its color. It absorbs light, particularly around 420 nanometers. So down in this range, 520 and 620. Those are 3 wavelengths that we will be looking at. We are also going to look at 280 nanometers because there is significant absorbance of ultraviolet light at 280 nanometers, significant absorbance by wine. So our spectrophotometer, we can set for a particular wavelength, and we can absorb all these wavelengths of interest. We could look at lots of others to look at different properties in wine, but we are looking at phenolic compounds in wine, polyphenolics, phenolic compounds, and these 4 wavelengths, and I'll mention them again, are key. So we're going to do 4 absorbances. I mentioned that the shorthand for absorbance is just a capital A. We're going to look at absorbance at 420, so we give that a subscript 420. We're going to look at absorbance at 520. We're going to look at absorbance at 620. And then we're going to look at absorbance at 280. So 280 measures total phenolics. So if there's a phenolic molecule in wine, and remember phenolics are defined by the fact that there's phenol somewhere in the structure, and phenol looks like this with alternating double bonds. So that's phenol. There's phenol somewhere in the structure, and every phenolic compound absorbs some light at 280. So that gives our total phenolics at A280. The other three tests measure our anthocyanins, our colored phenolic compounds. So that's what gives wine its color. So 420 would be in this range on the color wheel. If wine absorbs at that wavelength, what it means is when you shine white light on a wine, wine absorbs the light around 420, not just exactly 420, but around 420. And what we see is the opposite. So we see yellow at 420. I always say we see at 420. If wine absorbs at 520, that's absorbing in the green range. So we're going to see red when the wine is absorbing at 520, and that's 520 nanometers or 420 nanometers. So obviously 520 is going to be a big absorbance number because our wine appears red. So there's lots of absorbance of light around the 420 range. We look at just 420, but it gives us an idea of the intensity of the red. 620 is going to be in the orange range, and those are going to be pigments that make the wine give the wine a bluish cast. Okay? So each of these absorbances, these are different pigments that absorb different wavelengths. And pigments have different colors because of what they absorb. The light opposite to what they absorb is what we see. So we will test these four. We'll add up the three colored absorbances, and that'll give us our color density. And then the total phenolics is the A280 number. Now, what if other molecules absorb at the same wavelength of light? Because there are lots of molecules in wine. So, and potentially our cuvette, say, could absorb, or things in water molecules might absorb at those wavelengths. So, to correct for some of those absorbances, we first blank with water. All right, so we set our spectrophotometer, or Spec for short, to 0 when our cuvette contains pure water. I'll just say water. All right? Now, when we put the wine into the cuvette and get an absorbance, all the molecules in the wine are going to absorb as they normally would. And one of the ones that absorbs at A280 is protein. It's all the protein molecules that actually absorb at A280. So we have to correct for that. So normally, we could do a test of how much protein's in the wine, but we use an estimate. And we estimate that our protein absorbance is 4. All right, so we back out 4, subtract 4. I say back out. Some people have never used that term. It's kind of a lab term. We subtract 4 from our absorbance at 280. Okay, so we'll blank with water. Then when we get our results, after we read our results, we'll back out 4 from the A280 number. Okay, a couple of things we do. We're going to make 2 dilutions. We'll do a 10x dilution and a 100x dilution. The 10x dilution we'll use for the A420, A520, and A620 absorbances. The 100X we will use for the A280 absorbance. So 100X dilution would be 0.1 mils of wine with 9.9 mils of water. So 1 part wine and 99 parts water. To measure out accurately the amount of wine, the 0.1 mils, we're going to use the 20 to 200 microliter pipette. That has the yellow top in our lab. All right, we'll set that so it reads 100 or 100 microliters. All right, so set to 100 microliters, and that equals 0.1 milliliters. The 1000 microliter pipetter, we're going to have to set that to 1000, which on the pipetter itself reads just 100. There are only 3 digits, so the last 0 is left off. All right, so it's going to just read 100, but it's going to be 1000. So we'll dispense 9 times 1000 microliters of water, and then we'll set the micropipetter to 900, which will be 090. That's what it reads, and that will be 900 microliters. And we dispense 1 times 900 microliters. All right? And together then, that will give us 9.9 milliliters of water. All right, so we use the big micropipetter, the P1000, to dispense water. We use the P200, which is the 20 to 200 microliter micropipetter, to dispense our wine. All right, and we're going to have all of our absorbances. Remember, what we're doing here is we're measuring things like the softness index. Remember that from the prior slide, the prior video. The softness index is a measure of the ratio of the color density to the total phenolics. So if we add all of our color absorbances at 420, 520, and 620, we add, and that equals the color density. All right, so our worksheet, the worksheet you'll work on will ask you to add those up and give you and come up with a color density. The A280, this is going to be our total phenolics. In the nomenclature we used in the last video, that would be the same as our tannin index. If you remember the wine chemistry videos, I'm sure you're saying, wait, phenolics consist of tannin and colored compounds. And if this is total phenolics, it's not just tannin, it's also colored phenolics. And that's true. But we take that A280 for simplicity as our tannin index, as a good indicator of the total phenolics extracted. Okay. So we will measure these wavelengths. And I'll see you in lab, and we'll perform this experiment. Thanks for watching.